All right, here we go.
It's cheese clusters because guess who's in 4th hour tele?
Shut up, Evie. Not Matthew, my lab partner. Who am I supposed to laugh with?
He
You?
can switch back. And she's doing team sports.
Yes, I can get team. What hour? 6?
All right. So equilibrium, typically up to this point, except maybe when we had our discussion regarding weak acids and weak bases, we have had equations where this arrow is one direction and one direction only. Okay. At this point, we are kind of moving into this idea of equilibrium. And that's where the reaction runs in both directions. Why is this not letting me? Here we go. All right.
That was my basketball arm that I used. How am I supposed to play in the big game?
Although I did see somebody's name in the paper this weekend.
Thank you.
All right. So many chemical reactions don't proceed in only one direction from reactants to products. So just like you were throwing the paper, you were throwing it from both sides. One side was reactants, one side was products. Whichever side started out with all the paper at the beginning, that was the reactants. The side that was receiving the paper then was the products, and they were getting thrown back and forth. So if we had like a sealed bottle of water, the water can evaporate and condense within that bottle. So we call reactions that can go in either direction reversible, and we use these arrows to draw that in. Now, typically when we are writing these arrows, a lot of times we'll draw them like that. Okay, instead of drawing two arrows this way, we'll draw it like this because you can do it in one fell like pin swoop. And it just, I don't know, we're just lazy scientists, and so that's what we do. So that's typically the way you'll end up drawing it. It's like that. So examples of this would be like evaporation and condensation of water. That's reversible. Adsorption and desorption of gas by a solid. So, and that's going to be reversible. You'll also see it drawn like this sometimes, depending on what software people are using. So dissolution and precipitation of a solid in a solution would be like this, where it's getting mixed in the solution and then it's precipitating out. Proton transfer in an acid-base reaction, or electron transfer in a redox reaction. So in a reaction that is reversible, will eventually reach a state of dynamic equilibrium. And that's what we ended up with over there, where we always had two on that one side, unless somebody cheated, Allie.
Cheater.
So forward rate of the reaction is equal to the reverse rate of reaction. It does not mean that the amounts of the reactants and products are equal. They were not equal there. We had 58 on one side and 2 on the other, but it was consistently the same on both sides after the reaction began. Does that make sense? So equilibrium does not mean that you have equal amounts of products and reactants. One side might be favored over another one. One side may have more than the other side does. The equilibrium is dynamic, which means that the reactants and products are constantly being formed, but they're doing that at the same rate. There's still a reaction going on. There's still stuff being traded back and forth between the sides. There's still there's still paper being thrown back and forth. It's just the amounts on each side are staying consistent. That makes sense? We can graph the changes to the concentration of the reactants and the products as the reaction proceeds to equilibrium. So typically, you will start out a lot of times with 0 products, and you'll have some amount of reactants. The amount of reactants will diminish as you are forming the products. But eventually, they will level off here, and their amounts will be consistent. Good?
Yes.
So where you've established equilibrium is where these lines on the graph are straight. Is that 0 slope? Is that what that means in mathy terms?
For sure.
Okay. All right. You guys have to help me once in a while with mathy terms.
I won't be much help, but me neither.
How was that at 98?
Yeah,
that's
I did.
Malarkey.
Oh,
What's your group?
it was so
Jordan
funny.
Thompson and Ben Ard.
Because Mr. Macho came over and he's like, Allie.
All right.
I knew this was-
We're starting with our reaction with 1 atm of A, 1 atm of B. There is no C and D. That's our products in the flask. So they want us to show how the reaction is going to proceed upon reaching equilibrium where there's 0.8 atm of A. So we have one of these, we have one of these, 0 and 0. So if we do kind of a table over here, so A plus 2B yields C plus D. Now, we are going to have, these are called ICE tables. You're used to your BCA tables, right? These are ICE. So, what do you think that the E stands for?
Equilibrium.
There you go.
I knew it. I bet you said that.
So E is equilibrium. C is the same as what we've been having CB, which is change. This is initial. So initial, change, equilibrium. These are starting out at 1.0. They said that there's none of this there. They said that when we were done, that A was 0.8. So what was my change for A? 0.2. What would my change for B? 0.4. And then I'm going to be subtracting that because we're using that up
Wait, how do you know it's 24?
because it's in a 2-to-1. Guys, it's in a 2-to-1 ratio. So for every 0.2 of these, I have to have 0.4 of these. Does that make sense? All right. How much am I going to make? Guys, how much am I going to make of this guy? 0.2. And what about my D? 0.2. Okay. So at equilibrium, what is B going to be? 0.6. And these are both going to be 0.2s. So we should be able to graph this now. So for A, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is my 1.0 here. This is my 0.8. That makes this 0.6. That would make this 0.2. Okay, so I got everything labeled that I need. For A, I'm going to do A in this color. It's going to go from 1, and then when we hit equilibrium, it's going to be here. And then it's going to steady off. That's a great straight line. Thank you. Thank you very much. Oh, it won't let me change colors. Sorry. Yeah.
I hate this app.
We're supposed to learn.
All right. So B, I'll have to do just dash or something for B. B is going to end up at 0.6, where it's going to be consistent. Okay. So I'm going to do him as kind of a dashed line. Okay, so that's my straight line for B. So he's going to be a dotted line.
Oh,
And then C and D start out at 0,
I'm going 0.2.
and then they're going to go to 0.2.
Thank you.
And this is C and D, which I try to do as more of a dashed line that way. Does that make sense? Does that work for you guys?
What is that?
All right. So
No, I'm actually kidding.
they want us to write an equilibrium reaction for this process, the freezing and melting of benzene. So benzene is freezing and melting. So that means that it's going to be a solid on one side. So solid. And then benzene, oh, this is supposed to be a 6 here. C6H6. And then over here, it would be what?
Liquid.
A liquid. Yep. There it is. Done. Make sure that you have a 2-headed arrow. All right. Dissolution of a weak acid, HCN. So that means that it's going to start out as aqueous. Yep. So we're going to start it out as aqueous, and once it gets in that aqueous form, it's going to disassociate from itself. So what's the other part going to be?
CN.
CN what?
Solid.
No,
Liquid. CN2. Yeah.
no.
CN aqueous.
CN aqueous. I'll buy that. What else do I need on there?
A negative.
Yes. There you go. All right. So this broke apart into ions. Proton transfer between the weak base, HS, and the weak acid, H2PO4. So HS minus AQ plus H2PO4 minus AQ. Which one's going to lose their hydrogen? First one?
H2PO4.
Why do you say that?
Because it has 2 hydrogens.
No, that's irrelevant.
Weak acid.
Exactly. It's the
I knew
weak. It
that.
was identified as the weak acid. So if it's identified as the weak acid, that means that that's the one that's going to lose the proton or the hydrogen. So this is going to gain that. So it's going to be H2. What is its charge?
Positive. Just kidding, it's negative. It's not.
And you're wrong on both because it's neutral. It gained 1 positive, so it's nothing. Oh, yep. Okay, so this one becomes HPO4 what?
Plus.
2 minus. There we go.
How do you identify the weak acid?
Yes, 2 minus. What?
It said weak acid in the problem right here. All right, so that is my intro to equilibrium.
Is anybody else in physiology sports?
9-1 is due tomorrow after